Welcome back, everyone. In this lecture, we're going to discuss the normal distribution. Now, the normal distribution is probably one of the most important distributions in all of statistics. It creates the foundation for hypothesis testing and inferential statistics. So it's important that we take a little bit of time to step back and understand what the normal distribution is all about. So in this lecture, we're going to start off with talking briefly about the importance of the normal distribution in the realm of statistics. We're also going to go through and cover some of the key characteristics that the normal distribution has and talk about a few examples of the normal distribution. As you're going to see, even though it's called the normal distribution, it's actually a family of distributions. And a lot of distributions can have what we would call a normal distribution shape. But we'll see that in a few moments. Also in this lecture, we're going to talk about how the normal distribution plays a key role in assisting us as sort of as a bridge into hypothesis testing and inferential statistics. And this is where we're going to talk about something called the sampling distribution of the mean. And the sampling distribution of the mean is a theoretical probability distribution. And we're going to talk about how to construct this theoretical probability distribution, as well as also covering three important characteristics of the sampling distribution of the mean. Now, one thing that I will warn you about is in order to make sure all the material you need in order to understand the sampling distribution of the mean, you will see that some of these slides are very wordy. Definitely not what I would call like the proper style for a PowerPoint presentation, but I want to make sure that the material is there. So even though you're going to see a lot of words and a lot of information on some of these slides, bear with me because I will do my best to sort of hit the highlights, point out the key facts that you really need to know about both the normal distribution and the sampling distribution of the mean. So let's go ahead and get started. So what makes the normal distribution important? Well, on this slide, we're going to cover just a few of the things that make the normal distribution important in the realm of statistics. First off, a lot of population distributions are assumed to follow a normal distribution. Things like height, things like weight. And what do I mean by assumed to follow a normal distribution? Think back to when we talked about the shapes of distributions a couple lectures ago. Right? A normal distribution, as we'll see in a moment, is that sort of that symmetric bell-shaped curve. And a lot of things that we study, both about human behavior, human characteristics, as well as other scientific fields, a lot of things we measure tend to have that sort of bell-shaped distribution. Therefore, the normal distribution has been studied extensively, and therefore it plays a central role in statistics. So much so that as we move forward, we're going to talk about how we start to talk about the standardized normal distribution, and we'll talk about different sort of standardized distributions like the Z distribution, the T distribution, the F distribution, and others. So this normal distribution that we're going to briefly mention today is often referred to as the parent distribution of many other statistical distributions. And we'll talk about those other distributions later on in the course. And then finally, the normal distribution has a close connection to something called the sampling distribution of the mean. And this sampling distribution of the mean is really what allows us to effectively use sample data in order to draw conclusions or make inferences about the larger population. And that's the backbone to inferential statistics. So we're going to see how the normal distribution is closely connected to this thing called the sampling distribution of the mean, and also one of the characteristics of the sampling distribution of the mean, and that's known as the central limit theorem. One thing to remember about the normal distribution, even though we call it the normal distribution, there's not just one normal distribution. Rather, we can think of them as a family of distributions where the central point of the distribution may change or the overall width, the variability, the standard deviation may be different. But all normal distributions have similar characteristics, and we'll see that here in just a second. Another thing is we often refer to the normal distribution as a two-parameter distribution. What do I mean by a two-parameter? Well, if somebody says, oh, we're working with a normal distribution, and if I need to know what it looks like, I need to know two important characteristics of that normal distribution. I need to know the mean, and I need to know the standard deviation, because that will tell me where is it centered about, and also how wide is it typically. So you can see here, we need to know mu, the population mean, and sigma, the population standard deviation, to identify the particular normal distribution we're talking about. But all normal distributions share three characteristics. They're symmetric, they're bell-shaped, meaning they're unimodal, and the mean, median, and mode are all at the same point. Okay, so on this slide, you may be going, I'm already lost. We just got started. We're on slide 3. Don't worry about it. On the next slide, what I'm going to see, and look down at the bottom of this one, I am going to show you just some examples. Let's take it back a step. I'm going to show you examples of 4 different distributions. All 4 of the distributions on the next slide are what we would call normal distributions. But when you see them, you'll know they're not the exact same distribution, but they all share those 3 characteristics that we see here in point 3. So let's take a look at the next slide and see how they illustrate these various characteristics that we have listed on this slide. So here are several examples, 4 examples of normal distributions. And you'll see whether it's the pink, the red, the green, the blue, they are not the exact same distribution. They vary in their height, in how wide they are, and also where they are centered, where the middle point is, right? But they all share those symmetric, bell-shaped, unimodal characteristics that make them normal distributions. You'll see here that the blue, the green, and the red all share the same mean. They all have the same middle point, but they have varying heights and widths. And then we have that purplish, pinkish looking one, which differs from the other 3 in the fact that it not only does it have a different sort of width and height, but it also has a different sort of mean, a different central point. So even though each one of these is their own unique distribution, we would call each one of them a normal distribution. So now that we have a brief understanding of what normal distributions are, we can move on to a very important sort of application of the normal distribution and the characteristics of the normal distribution. And so now we're going to transition into talking about something called the sampling distribution of the mean. And this is where when I started this lecture, I said, hey, get ready because there's going to be a lot of words. Well, welcome to this slide. I apologize for all the words, but I'm going to highlight what is really important. Okay, so let's talk about this. What is a sampling distribution of the mean? Well, first and foremost, it is a theoretical probability distribution. What do I mean by theoretical? Well, for more often than not, you don't really ever see or create a sampling distribution of the mean, but statisticians for a very long time have been using the characteristics of it in order to understand the probability of any particular sample that you may draw from a larger population. So let's look at our second little bullet point here. What does it say? It says, the sampling distribution of the mean provides information about the relationship between the possible values of sample means and the probability associated with each possible sample mean for all possible samples of size n drawn from a single population. Wow, okay, that is a mouthful. What the heck does all that mean? The bottom line that this is saying is what this theoretical distribution allows us to do is it allows us to figure out what is the likelihood of us getting any particular sample from a larger population. So let's take a step back, and we'll see it more as we go forward, but let's take a step back for a second. As researchers, we want to study the world around us, right? We want to draw conclusions and answer questions about the populations around us. But as researchers, we rarely ever get access to an entire population. We get access to small pieces of the population known as samples. So as a researcher, I go out and collect data from a sample of humans. But I need to know how representative is that sample of the population that I think that they're supposed to have come from. Do I have a rare sample? Do I have a common sample? Are they representative or are they not representative? That's what this sampling distribution of the mean allows us to do. It allows us to start to quantify and get sort of an objective measure of the likelihood of me getting a representative or a non-representative sample from the larger population. So let's take a closer look at the point that says key use. So this is kind of re-summarizing what I just said. So when conducting research, we only have access to one sample of any particular size. And that's why you'll hear the size n and things like that as we talk about the sampling distribution. So I get one sample. Maybe it's 50 people, maybe it's 100 people, maybe it's 1,000 people. But I only get one sample. And that's one sample out of all the possible samples that could have been drawn from the population. So, and we're going to go through an example in a few moments. In that example, there are going to be 16 possible samples, but as a researcher, I would only have access to one of them. Now, as a researcher, I don't know, did I get a sort of a representative sample or did I get a really odd sample? I need a way to quantify that and measure that. That's where the sampling distribution of the mean comes back into play. So the second bullet point under key use. This is where we think about, is our sample what we'd call a rare sample? And I say, in other words, out in the tails. That'll make sense in a few moments. Or is it a common sample, meaning that it is a typical, a representative sample of the population it came from? So real quick, before we jump ahead, let's rethink that one last time. So imagine if I go and I'm asking a bunch of students, say in our class, say we have 40 students in our class, and I want to survey 4 students to figure out how well they're liking the class. Now, ideally, if I only pick 4 students, I may, by dumb luck, I may get a representative sample. I may get students who give me good feedback about the pros and cons of the course, and then the feedback I get from those 4 students, my sample, are representative of the overall feelings of the entire population of 40 students. But when picking those 4 students, what if I happen to pick the 4 students who hate statistics, don't like me as a professor, are fed up with school, or for whatever reason have nothing but negative feedback to provide? Now, those students, I may walk away and go, wow, my entire population, my entire class doesn't like the course, doesn't like me, but that is not necessarily representative. You kind of get the idea. That would be a rare sample. And that's what this sampling distribution of the mean allows us to start to figure out and quantify. And so let's move back down to the second bullet point under key use once again. So do we have a rare or a common sample? Why is this important? Well, this concept provides a foundation for deciding whether our sample results are likely or unlikely to be due to chance. And you're going to hear me use that word as we get into hypothesis testing and inferential statistics. And being able to quantify common versus rare, sample results that are accurate or due to chance, that's the foundation for hypothesis testing and inferential statistics. As we will be talking about in future lectures, we know that as researchers, that if I focus on sample data in order to answer questions about the larger world or the larger population, I know I'm not going to always be 100% accurate. That's the nature of the game with statistics. You're never going to be 100% accurate, but you still want to have an idea. Am I certain with 95% certainty or 80% certainty? And that's where this thing's going to come into play. All right, Final thing before we move on and start talking about how we actually construct a sampling distribution is make sure that you read the final little like asterisk point down at the bottom about probability. Now I know in other statistics courses, they will spend a whole lot of time talking about probability and the different formulas for, figuring out the probability of some outcome or event occurring. For the sake of what we're talking about right now, I just want you to have a general understanding of what is probability. And so in its simplest sense, probability is the proportion or fraction of times that an outcome or an event will occur. So if we have a coin, right? There's a heads and there's a tails. What's the probability of flipping a coin once and getting heads? Well, there's two possible outcomes, heads or tails. So it's a 1 out of 2 chance, which is 50%. So that's the probability. What is the probability of drawing a heart card out of a deck of cards? So assuming I have a deck of cards with 52 cards, no jokers, there are 4 different sort of suits. One of those happens to be the heart. There are 13 hearts out of 52, which gives me a 1 in 4 or a 25% chance of dealing a heart card. So if you understand that sort of level of probability, you'll be fine with the rest of this lecture. So let's go ahead and jump in. In order to think about how we would construct a sampling distribution of the mean, we have to start at the beginning. And the beginning is a scenario. So roll with me on this one because I sort of made this one up. But let's imagine that our population, so that's why I kind of keep it this way, our population consists of 4 people living on a desert island. So that's it. The entire population of people on this desert island is a total population of size 4. So not very big, but that's what we need to do in order to do this little thought experiment. Each person, each one of those 4 people in the population has a stash of coconuts. Why? I don't know. Maybe they're tasty, they like them, they're healthy, who knows what. But each of those 4 people has a personal stash of coconuts at their little hut, their little house. Okay. Person 1 out of the 4 living on the island, person 1 has 8 coconuts in their stash. Person 2 has 9 coconuts. Person 3 has 10 coconuts. And finally, person 4 has 11. So quickly to recap, the entire population of individuals on this island is 4 people. Each of those 4 people has a stash of coconuts. And then as we see in this second bullet point, I tell you how many coconuts each of those 4 people has. So when I look at the actual population of people living on this desert island, here is sort of what the frequency distribution and the histogram for the population look like. So let's start with where it says population frequency distribution. There was the number of coconuts that were in the possession of an individual. 1 out of 4 people had 8 coconuts. 1 out of 4 people had 9 coconuts. 1 out of 4 had 10 coconuts, and one of the individuals had 11 coconuts. That is the entire population. I plot that population data into a histogram. And you'll see that down there with the chart, the histogram down at the lower right. And we see that it says population. There's a bar for 8, 9, 10, and 11. But the frequency is only 1, right? There's only 1 person that has each one of those things. Okay. That is where we start with. That we know this is why it's important in this thought experiment. This is truth. This is the reality of the population. So the population looks like what we see in that histogram. So there's 2 things I want us to take away from that histogram. The first, and probably the most important, is what is the mean? What is the average number of coconuts per person? And the mean for that population is 9.5. So make a mental note of that. The true, undisputed mean for the population is 9.5 coconuts. Okay, so we have that. Now, Also look at the shape of that histogram. It's flat. Yeah, it's symmetric. Can't really say if it's unimodal, whatever. It's kind of unexciting, right? It really doesn't have any curve or shape to it. It's just flat. So remember that. Does that look like a normal bell-shaped curve? No, it does not. So the two things to take away from that histogram, the most important is the mean of the population. The true mean of the population is 9.5. Make sure you remember that. Second thing is the shape of the distribution is not a normal bell-shaped curve. Rather, it's just a flat curve, or a flat distribution, I should say. All right, now let's jump into constructing a sampling distribution of the mean from this population. So how am I going to construct a sampling distribution of the mean? I told you early on that I would highlight the important stuff, kind of like what I did on the last slide when telling you about important characteristics of the population. The same thing goes for this slide. This slide is important. I'm never going to ask you to actually construct a sampling distribution of the mean, but you should understand sort of the steps that go into it. Okay, so how do I construct a sampling distribution of the mean? Well, first of all, you have to know something about the population. So we've already talked about that on the previous slides. We have a population that has a total number size of 4 individuals, one person with 8 coconuts, one person with 9, one with 10, one with 11. What I'm going to do in order to construct my sampling distribution of the mean is I'm going to draw or figure out all possible samples of a certain size. So the size that I've chosen to do for this experiment is of size 2. So I'm going to draw all possible samples of size 2 from that population. Then I'm going to compute the mean for each one of those samples. Once I have computed the mean for each sample, I'm going to plot those means into a distribution. So I'm not going to be plotting individual values. Rather, I'm going to be plotting sample means into a distribution. Once I have done that, ta-da, I have created what is known as a sampling distribution of the mean. So a sampling distribution of the mean is a distribution of sample means of all possible samples of a certain size. And if you look at these steps for constructing, you see that that language kind of comes through. It is a distribution of the sample means, all possible sample means of a particular size. So before we get into it, let's just make sure we all understand. So let's say that I hire you. Let's say I'm doing something where I want to figure out a source for purchasing coconuts from people who are living on a desert island. So I hire somebody. I tell you to go row a boat or sail a boat out to this desert island. And I say, I don't have enough money or time for you to get information from the entire population of people living there. We only have time for you to talk to a sample of the inhabitants of this island to figure out how many coconuts they have in their stash. So you row your boat up to the shore of this island one night, you go ashore. Let's say the first person that you come into contact with, you say, excuse me, sir, or madam, or whoever it may be, how many coconuts do you happen to have? And they look at you and they may say 9, right? Because one of those people has 9. Okay, so you write that down, 9. And then you walk around the island a little more, you come across somebody else, and you ask them the same question. Excuse me, sir or madam, how many coconuts do you happen to have at your house or your hut? And they say 11. Okay. So now you have a sample of size 2, right? You have the first person in your sample had 9 coconuts. The second person had 11. So when you all of a sudden take your data and row your boat all the way back home to me, you say, okay, I got my sample of people and I asked them about their coconuts. And I say, well, what did your sample data look like? And you say, well, I talked to 2 people, a sample size of 2. I say, okay. You say first person had 9 coconuts. the second person had 11 coconuts. So I say, okay, well, let's figure out what is the average for that sample. 9 plus 11 gives us 20. 20 divided by the sample size of 2. 20 divided by 2 is a mean of 10. Okay, so the sample mean for that one sample is 10. Now, think back to what you saw in the previous slide. Is 10 exactly the same as what the true population mean was? No, it's not, right? The true population mean was 9.5. Now, we by dumb luck got one sample. Our sample said that the average was, or the mean was 10. So it's not a perfect reflection or representation of the population, but it's also not too far off, right? It's only a half coconut off. That's why we have this thing called the sampling distribution of the mean. In the steps and slides that follow, we're going to see that it allows us to objectively quantify the likelihood of getting a sample like we just saw, that one that had a mean of 10. So it allows us to start to get our mind around, like, what's the likelihood of us getting something that's only a half coconut off versus a rarer or a more representative or common one. So let's go ahead and take a look at how that works going forward. Let's look at all the possible samples of size n equals 2. On this slide, you see all possible samples of n equals 2 that we could have drawn from that population. So remember, the population had 4 people, one with 8 coconuts, one with 9, one with 10, one with 11. Just like I described on the previous slide, imagine you go out there as a researcher, but you only get to talk to 2 individuals. Your sample is only 2. Here on this slide, we see all the possible breakdowns, and there's 16 of them. So what you see here is, if you want to look at sort of the numbers in the charts on the bottom, the values show us the coconuts for each of the 2 people in each possible sample. So you see an 8 and an 8, an 8 and a 9, etc. And you may go, wait a minute, Ryan, why do I see an 8 and an 8 when there's only one person in the population who has 8 coconuts? All right, sidebar for the little statistical jargon. This is known as sampling with replacement. So in order to do this theoretical thought experiment, you have to assume that if you draw one of the people out of the population to be part of your sample, that they are thrown back into the population before you reach in and grab your second sort of case for your sample. So it's called sampling with replacement, and that's why you'll see when we look at the values, you'll see an 8 and an 8, a 9 and a 9, a 10 and a 10. Don't let that get you confused or overthink it. The simplest way for me to think about it is when I told you, if you were my research assistant and I said, go to the island, row your boat there, and talk to 2 people and ask them how many coconuts they have. Imagine you did it in the middle of the night with no flashlight or anything. So you walk up to somebody on the beach and you ask them, how many coconuts do you have? And the person says, 8. Great, thank you very much. And then you go walking down the beach and you can't find anyone. You turn back and you walk back up the beach and you see a human, and you don't realize it's the same person you talked to, but you walk up to this person and go, how many coconuts do you have? And they go, 8. And they're probably thinking, what, you just asked me that 5 minutes ago. But all that aside, that's sampling with replacement. Okay, sidebar over. Let's bring it back to these 16 possible samples of size 2. So we have all of them listed. So 8, 8, 8, 9, 8, 10, 8, 11, 9, 8, 9, 9, 9, 10, etc. And there's sort of, the 2 major columns of there. Then, in order to compute or construct a sampling distribution of the mean, I need to compute the mean for each one of those samples. So when you look at these columns, that's sort of the second little column within each one. You see the mean for that particular sample. So like 8 plus 9 divided by 2 is 8.5. 8 plus 10 divided by 2 gives me a mean of 9, etc. And then the probability of me showing up at that desert island and getting any one of these possible samples is roughly 6.25% likelihood, right? Or 1 out of a 16 chance of me getting any one of those samples. All right, so what have we done so far? Well, we figured out the size of the samples that we were going to focus on, which is samples of size 2. We have gone out and collected data from all possible samples of size 2. We move on to the next step for construction. We have computed the mean for all possible samples of size 2. Now we need to consolidate that information and get it ready to be presented into a distribution. So on this slide, what I'm doing here, what you see here is I've consolidated all of the sample means from the previous slide. You'll notice I'm no longer focusing on individuals and each individual's coconut stash size. No. Now I'm only focusing on sample means. So there were 16 samples that I saw in the previous slide. And what I've done here is I've condensed all the sample means. So there was only one of the 16 samples that had a mean of 8. There were 2 of the 16 samples that had a mean of 8.5. There were 3 of the 16 samples that had a mean of 9.0. There were 4 that had a mean of 9.5, and etc., all the way up to one of the sample means had a mean of 11. So I've consolidated all the sample means out of the 16. I've shown the probability of getting any one of those particular samples just by dumb luck or in a random sense. Now let's plot each one of these into the distribution. And ta-da, there we have it. This is our sampling distribution of the mean. This is a distribution that represents the sample means of all possible samples of size 2 that were taken from that population of individuals living on that desert island. So let's slow down and think about what we can take away from this. First and foremost, do you notice the shape of this distribution? Hopefully you're starting to go like, wow, yeah, it is. It's starting to look like that nice, symmetric, unimodal bell-shaped curve. It looks like a normal distribution. And I'll give you a hint right now. That is not due to dumb luck. This is a statistical fact, which makes this thing called the sampling distribution of the mean kind of cool. The fact that it does approximate a normal curve. So that's one thing. So the shape of it, pay attention to that. 2 is let's take a look at the mean of this distribution. And you can see it written down there on the right-hand side next to the histogram. And you'll see that the mean of this particular distribution happens to be 9.5. When did we hear the mean 9.5 before? Yeah, it was the population mean. So once again, is it by dumb luck that the mean of the sampling distribution of the mean happens to be exactly the same as the mean of the population? No, that is not dumb luck. That is another statistical fact. So, final thing to take away with this before we move into the characteristics and kind of rehash some of the things I just said is, what has this done? Well, I started off with telling you that the sampling distribution of the mean gives us a way to sort of quantify the likelihood of getting either sort of a common, meaning a representative sample of the population, or a rare, a non-representative sample. So looking at this, remember the true population mean of coconut stashing was 9.5. Well, we happen to have 4 out of the 16 possible samples we could have chosen from this island are perfect representations of the population. 4 of these samples have a mean that is 9.5. Boom, 100% bullseye, perfect representation of the population. Then, if we're thinking about something being just a little bit off, like close to being a perfect representation but not quite perfect, Let's look at the 9s and the 10s, only a half point away from the true population mean. There are 3 samples of that had a mean of 9. There are 3 samples that had a mean of 10. So we've got, that's another 6. So 6 plus 4. So we've got 10 out of our 16 possible samples that we could have stumbled upon are pretty darn close to the true population mean. But as the way it works, whether you're gambling, whether you're doing research, it's just the way the world works. There's always that possibility we could just, when we show up and we collect data and get our sample, we could have gotten what we would call a rare sample. Now, the likelihood of getting that rare sample is much lower than it is of getting a common or a representative sample, but it's still a possibility. And sure enough, we'll notice that there are 2 samples that are what I'd call pretty darn rare, right? There's one sample that had a mean of 8, and there's one sample that had a mean of 11. Those don't look much like the 9.5, the true value. So they are what we would call rare samples. So this is kind of that idea to illustrate what I mean, how the sampling distribution starts to give us an opportunity to quantify the likelihood of getting any particular sample and getting an idea of what's the possibility or likelihood of us getting what we call a common or a rare sample. And we'll quantify this further in one of our upcoming lectures once we start talking about something called the standardized normal curve, and we talk about computing the area under it. But let's not get too far ahead of ourselves. So for right now, let's go through and let's wrap up this lecture with talking about 3 important characteristics to take away from the sampling distribution of the mean. You heard me say this a couple times, but let's go ahead and make sure that we know it and know it well. The mean of the sampling distribution of the mean will always equal the mean of the population. And that's what we saw with this little theoretical experiment, right? The mean of the population, many slides ago, we saw was in fact 9.5. That is the true undisputed value of the mean. And we also saw that once we constructed that sampling distribution of all possible samples of size 2, the mean of that distribution was also 9.5. And this is what allows us to start to think about how we can use samples to tell the story of what's going on in the larger population. So the mean of the sampling distribution of the mean will always equal the mean of the population. A second characteristic of the sampling distribution of the mean was also mentioned on previous slides. I didn't give it the fancy name, central limit theorem, but now I will. So think about the shape of the distributions we saw. We saw the shape of the population distribution. Remember, it was symmetric, but it was just flat. Then we saw that shape of the sampling distribution of the mean, and we saw how it had that nice symmetric bell-shaped curve. All right, this all ties into something called the central limit theorem. And this says that regardless of the shape of the parent population, it just means the shape of the population, the sampling distribution of the mean will approximate a normal distribution. And that's exactly what we saw. And then you'll also see under the central limit theorem, I say in parentheses, once the sample size is sufficiently large, and in most cases that is true. Working with a sample of size 2, with a much larger population, not a population of 4, but a population of 400 or 4,000 or 4 million, a sample size of 2 is not very large, and this may not play out. But don't worry about that. I'm not going to try to fool you in this course with some sort of like sample size issue, but I wanted to make sure that you have the full definition there, just so you have it. So once again, the central limit theorem says that regardless of the shape of the population, a sampling distribution of the mean will approximate a normal distribution. And we saw this. So I say, look at the shape of the population distribution several slides earlier. Was it symmetric? Yes. But it was flat. So it wasn't bell-shaped. No, it wasn't. And then when we looked at our sampling distribution of the mean, it was both symmetric and bell-shaped. And then finally, the third characteristic of the sampling distribution of the mean has to do with sort of the width of the sampling distribution of the mean. Now, I have not mentioned this one quite yet. This one will make a little bit more sense to us as we start moving into the standardized normal curve in the next couple lectures, but I wanted to point it out to you. And also it gives me a chance on the next slide, you're going to see another version of a sampling distribution of the mean drawn from our same population of 4 people living on a desert island, and you'll see how it maintains several of the characteristics that we've discussed so far. But before I get there, let's talk about this thing. So as the sample size increases, so we took all possible samples of size 2. But if I had instead increased my sample size, so say all possible samples of size 3, then what happens is the overall width of the sampling distribution of the mean shrinks. How do we measure the width? We measure it with something called the standard error of the mean. So as sample size increases, the standard error of the mean decreases. Why is this good? Well, it gives us more precise estimates about the population. Why? Because all possible samples are going to be closer to mu. Remember, mu is the population mean. And it kind of makes sense, right? Let's put all the statistics aside for a second. If I simply asked you, what type of sample is more likely to be an accurate representation of the population? So once again, if I were to ask you, what type of sample is more likely to be an accurate representation of the overall population? And I gave you 2 choices, a small sample or a large sample. I think we would all agree that all else being equal, a larger sample size is more likely to be an accurate reflection or representation of the population. And that's all this characteristic is telling us. It's just doing it mathematically. So as the sample size increases, the standard error of the mean decreases. All right, and then what is the standard error of the mean? Let's look at a couple of these final bullet points down at the bottom. We'll be talking about the standard error of the mean in more detail in later lectures, but for right now, let's just mention a few of these things. It is a rough measure of the average amount by which sample means deviate from the mean of the sampling distribution of the mean or the population mean, because those are both equal to each other. It is a roughly equivalent to the standard deviation of the sampling distribution of the mean. So remember when we talked about a standard deviation before, we talked about the standard deviation gives you a rough idea of the average amount by which values deviate from the mean. That's exactly what the standard error of the mean is doing, but it's just doing it not with individual values, but with sample means. And then finally, we see the formula for the standard error of the mean, and it is sigma, the population standard deviation, divided by the square root of the sample size. And once again, we will see that formula put to use in a future lecture. So let's take a look at what would happen if we had computed a sampling distribution of the mean of all possible samples of size 3 from that same desert island population. And here we have it. This is what the sampling distribution of the mean would look like if instead of all possible samples of size 2, we said all possible samples of size 3. And as this starts to go, it exponentially gets much larger. So there was only 16 possible samples of size 2. So like an 8 and a 9 and a 10, a 10 and 11, etc. But there are 64 possible combinations of samples of size 3. So that'd be like an 8, a 9, and a 10, an 8, a 9, and 11, a 10, a 11, and a 8, I don't know, whatever. Any sort of combination of 3 from that original population. There are 64 possible, but this is what the sampling distribution would look like. And notice, once again, the mean of this histogram, this sampling distribution, still is 9.5. Same idea. That's a characteristic. The mean of the sampling distribution will always equal the population mean. Two, notice the shape of this. The shape is bell-shaped, symmetric, unimodal. Now, is it a little bit more condensed, like narrower together and taller? It sure is. That's where this third characteristic comes in, that the standard error of the mean has actually started to decrease for this particular sampling distribution because we have increased the sample size. Okay, so I'm going to wrap it up for there. I hope you kind of get the general idea. The key things to take away overall from this lecture are, if somebody were to ask you, meaning me, what is a normal distribution? You should have a general idea of what the normal distribution is. What are the characteristics of any normal distribution, right? And knowing that it's a family of distribution. Any distribution that is bell-shaped, symmetric, unimodal, etc., is a normal distribution. What should you take away about the sampling distribution of the mean? Well, one, you should have the general idea of its importance as being a theoretical probability distribution that sort of quantifies the likelihood of getting any particular sample from a larger population. Know those steps of how we constructed it. Remember, there's only like 4 or 5 steps for constructing a sampling distribution of the mean. And then definitely these 3 characteristics of the sampling distribution of the mean are going to be important, and I will probably continue to refer back to them as we move on into future lectures. So that's it for today. Take care and have a good one.